thank you very much, the organizer, to invite me, because it's a great pleasure to be with your friend Gianpietro, to honoring your retirement. So when they asked me to present some work, I did with Gianpietro, I think first that the work we published last year on the unified formulation on adhesion, and it has been published in the European Journal of Mechanics, giving a unified formulation for adhesive model and cohesive zone models. And there was this opportunity too, and finally I showed this one. That's a work of thesis of Giampiero Pampolini, who is in the room. Where is Giampiero? And it was a thesis in co-tutelle between Ferrara and Marseille. And that's a study on the modeling of the open cell polymeric forms. I was more familiar with contact mechanics, but there is some connection with that. I will say a few words about that. And so, the problem, I think this is for interest for the student to spend the week at this course, because in this study there is all the different steps there is in a mechanical study. We start from experiment, we look for models, the ingredient we need to put in the model to fit this phenomena experimentally observed. There is the discretization and the simulations, the identification of the parameters, and that's a step which is sometimes underestimated, and the validation of the model on the complex simulation of the simulation of complex experimental processes. So, just the first thing we have on polymeric forms is phenomena of localizations. There you have the sample under the machine. We apply cyclic compressions, and there is, you see on this picture, the localization there, and there, and there is a movie of that. Here we are. That's a cycle, and we see the compression, the localization there. It's clear. So the first thing is we have localization of the deformations. And when we uncycle and when we unloading, we have the same phenomena, and we will see this on the curve on the stress versus the deformations too. Here. So first things, we'll look at one cycle, but there is some hysteresis, of course, with some residual stress and strain. So that's the first thing we can observe on one cycle, but that's just the beginning, because if we do several cycles, that's a surprise that at the loading there is a big difference between the first and the second cycle, and at unloading it's more or less the same always. So that's the second characteristic of the behavior of the forms. I want to say that in that study, the objective was not to give a 3D simulation with finite element of forms and anything like this. The idea was to understand what kind of ingredient the model has to have to describe this kind of phenomena. A second characteristic, if you do an experiment, that's the first, what I showed before, you put the specimen, you let it 2 days, and you take it again and you do a new experiment, and you obtain that time. There is some recovery after 2 days. And after 70 days, there is some change also, that the difference between that and that is some change. So, and we did experiment on more resting periods too. So that's a new element in the complex behavior of the form. If we do the cycle with different velocities, we get different cycles. That's just some tests with sub-cycles. And if we do some resting period during a cycle, we observe some relaxation phenomena. So we have a pretty complex behavior of the forms. Well, the first, or this model has been constructed step by step. The first one was to put nonlinear elasticity. That because of the localization was pretty obvious. So nonlinear elasticity with a non-convex stray energy, that one, and that gives this behavioral, the stress versus the deformations. We are working on a model, on one-dimensional models. That we have nonlinear springs here. We have to do with the cells of the, but just the models. The cells are not so regularly distributed. And so we will construct a model with a finite number of layers, and we are concerned of what kind of models to put for these layers. So first, nonlinear elasticity. So this, to build this curve, we combine two functions, this green function and Gaussian like this, just to fit that and that two function, and that's the form we have used to describe this behavior. And for that we have 6 parameters. 6 a lot, but we have to this stiffness, this maximum, this minimum, and the shape between the two. So we want to fit a lot of things in the experiment. Sorry. Now, before putting viscosity, we thought both about viscosity and damage, and we thought about, I talk about interface model and adhesions. I worked a few years ago on a model for recoverable adhesions, yielding adhesions. And at first, with Gianpietro, we thought that we can use that kind of models for the description of the behavior of the form. That's the reason we began to work on that. Finally, this turned out not to be convenient, and we turned to linear viscoelasticity first. So with that kind of models, that Kelvin-Voigt or the Senner models, that's for each layer and the global viscosity in parallel to everything. I will talk more about this model when I will talk about the identification of the parameters. And finally, we put some damage, and essentially to mark the difference between the first cycle and the second one. And we saw that for that, we act on the parameter C of these parameters, which characterize essentially the first stiffness. So, and that the curve sigma versus epsilon with 2 value of the damage. And so mainly these were the 3 ingredients we put in the model: nonlinear elasticity with non-convex energy, linear viscoelasticity, and damage. This has been, as I said, step by step, because At first we thought essentially about viscoelasticity, but it was not sufficient. So, the complete model is like that. That's the layers. That's the model in parallel. And we will see that we need several Kelvin-Voigt models to describe correctly the viscoelasticity, the viscosity of the models. So, what is the problem to be solved, and how we solve it? So the problem to be solved is that one. So that we have this condition that all the layers, that the total deformations, that the stresses, the stresses relate to the parallel modulus, and that relates to the nonlinear part and the viscous part. So we have to solve that problems, 1, 2, 3 equations, and these conditions, with the initial condition, of course, which is written there. We write an infinitesimal formulation of that. By differentiation of this relation, we got this incremental law. We can be written like that, with Qi equal to that and A high equal to that. Including this relation, we get this linear system on the velocities, where h depend on the current deformation. At each step, we have to build again the matrix H. So, but what happened because of the nonlinear? That's the way to evaluate A high and Qi. We don't compute the green kernel G, but we solve the differential equation associated to the Kelvin-Voigt models. These depend of parameter Pm and Km. We are related to decomposition in exponential series of solution. So to compute the coefficient of matrix H, we have to evaluate these two quantities written there. So that's the way to build the H matrix. When the determinant of H becomes 0, we got an infinity of solutions. So first, as long as the determinant is not 0, we just compute the regular solutions by solving the previous linear system. So there's no problems. And when the determinant of H is 0, when we got an infinity of solutions, an analytical analysis shows that the stable trajectory is given by the change of phase of one of the spring. That means that for a string, there is a jump on the second branch of the behavior law. The new equilibrium has to be computed at that time after that jump using Newton-Raphson methods, and we get again a system with a determinant H which is not 0, and we compute again as long as to get again these conditions and to have a second spring jumping on the second part of the curve. Just some comment about the role of viscosity. We have to note that determinant H is not 0 at that point where the derivative is 0, as it was the case if we are in elasticity, but there is a delay because of the viscosity. And that's just to understand what's happened. There is one spring going directly on the second branch, and we have to compute the equilibrium resulting of that after that jump. So that's the numerical simulations of one cycle. Depending on the number of elements you choose, and with 120 elements, it's pretty smooth. There is no difference. There is no anymore that kind of jump. That's a jump of each string. And that's just about the choice of the integration time step for the integration of the viscoelastic part. Now, about the identification on the constitutive parameters. That's a big point for very often, but in that case we have a lot of parameters and we have to pay a lot of attention, a lot of care to the identifications. So, to identification, the parameters relate to the viscosity. We have worked on other experiments than the cycles. We do some relaxation experiment on the forms. So we put stress heavy side, and we look at the, not at the contrary, an heavy side of the formation, and we look at the evolution of the stress, and we identify the parameters on this relaxation curve, both for the internal modulus and the one which is in parallel. So, mainly, we have just to have a look on, we have some relaxation curve, and we have to make an approximation of that through an exponential series. So we have to minimize that kind of functional, which is the error between the experiment measurements and the model simulations for an experiment of relaxations. We use Nuke-Jeeves methods, and just not a detail, but it's important when you do some identification work. We have to choose a good starting point for this kind of iterative methods. This is based here either on a logarithmic analytical analysis or Prony methods. I will say a few words about that, which is a way to get a good starting point for the identification of the coefficients. And that is of interest because the solution, the KG and PG, are not unique, you know, and so to have good initial coefficients with a mechanical sense, that's an important point. This Prony methods is pretty old, but not very used. It's just methods who give a series of n exponential going through two equidistant endpoints of any curve. And so we have to solve these problems where both the k and u are that part are unknown. And that's just a remark that the sum of exponential can be interpreted as a solution of the finite differential equation, this one. And from that we can compute the c and the c from the p, from that solution of the roots of the characteristic polynomial written here. And once we know them, we can put inside this system, which is then linear, and we get the solutions. That's how we used this method many, many years ago when I was a young PhD student. So, the identification of the viscosity on that give these parameters K and P. And we note that we have a lot. We need 5 modulus of viscosity, which is a lot. But we have to note that in the present problems, we have different scale of time. We have the viscosity at the scale of 1 cycle, and we have the viscosity about the recovering of the properties when we leave the samples for 10 days or more. So we have big range, and that's a difficulty too, and that's the reason we need 5 modulus of viscosity to describe conveniently the phenomena. Just to illustrate that, that's just the first part of the previous curve. That on the second curve is up on that point. And in green, that's the best we can do with 4 exponential. And that's just to underline that we need 5 in that case. So, once we have the viscosity parameters, we identify the parameters of the nonlinear elasticity, and then we work on a reference cycle test, or in reality of a mean value of several tests. Some of the parameters that the influence on the behavioral of the 6 parameters, C, mu, etc., M, beta, K, and A. Some of them are easy to identify directly on the behavior, as initial stiffness, for example. And we work like this. And the other one, we use again Ukenji's methods. That's after the identification of the nonlinear parameters, the simulation on one cycle. So in red the model, in blue the experiment. The damage. So for the damage, we need to work on the same reference cycle test, but now on 2 cycles, because the damage we will characterize the difference between the first and the second cycle. And that's for different value of the maximum of damage, and d equal 0.5 give a good description when we compare that experiment, and in green this curve is a choice for 0.5. So at that point, at that point we have the results of the identification of all the parameters. We have in green the models and in blue the experiment. And this gave a pretty good agreement between the model and the experiment. There is no surprise, the identification was conducted for that. But now we will have to work on the validation of the model, and that to check if with these parameters we get a good description of the behavior of the form when we applied more complex loading processes. But now the parameters keep the same. First, have a look on the localizations. Here is the curve that the column in the sample, in the forms. We have here the deformations, and at the scale between 0 and 0.7, and that for different points of the cycle, loading, unloading, reloading. At the beginning, we have an homogeneous deformation till that point. There, we have the localization, as it was previous. We was playing with the models. In C, the localization is progressing. There, all the sample is in the second phase. That means that all the cells are crushed. When we are loading, at first we have again an homogeneous deformations, and the localizations again at unloading. That's the point F. When we load again, we have again these homogeneous deformations, and in H we have again the localization, which is not so clear as it was at the first cycle. So this gives a pretty good description of what happened along the cycle in the solution. That's some tests with loading cycles with different amplitude. Here are the experiment, here are the simulations, and we see that we have a pretty good agreement between the experiment and the model. That's with other complex cycles. The experiment always on that side, with different amplitude of deformations, with a sub-cycle in that case, other sub-cycles, and we get a pretty good description with the model. That the recovery after waiting 2 days and 17 days, but again, we obtain a pretty good agreement between experiment and simulations. The rate dependence. The rate dependence will be something more complicated. We have experimental results for 3 velocities. For 2 of them, it works pretty well. Pardon. That's experiment, and that's models. But for the third one, there is a big difference between the simulations and the experiment. That means that we are out of the domain of validity of the models, and to extend the validity of the models to a larger range of velocity, we should introduce nonlinear viscoelasticity. Why? Because if we do another identification of the viscous parameters, we can find right parameters of the viscosity which fit the experiment. So that next step of the study, one is to build continuous models and not the series of springs. And another one is to extend the models to nonlinear viscoelasticity. That's all. And with all my best wishes and warm congratulations to Gianpietro in occasion of his academic but not scientific retirement, as you know. And I would like to say that I am very glad to work with Jean-Pierre and to know him 4 years now, and we share science, but also some visit in different places. And you know, I appreciate his huge historic culture everywhere. You visit a museum or a place with Gianpietro, and you get to know the history of the place for 2,000 years without any problems, and I'm very proud to be a part of the friend of you, Gianpietro. And he liked to go hiking too, and I do.